in tutorial 2, we extend what we did in tutorial 1. The differences being now we have simple shear loading as opposed to isotropic loading. The other big difference is that we are using an elastic plastic model, that being the Mohr-Coulomb model. I believe the elastic properties are the same. The difference now is that we have a friction angle. There's a series of questions. The first is some hand calculations. I talked about the importance of spot checking our results, and that's going to be highlighted in A. It's also useful to calculate values ahead of time and then compare the values calculated ahead of time with those that are calculated through FLAC. In many cases, it's the other way around. Next, once we do that particular question, now what we're going to do next is we are going to model the problem in FLAC. There's a question related to why does the shear stress increase after yielding? We'll talk about that. And then we're going to extend the problem to do a cyclic loading that goes from plus or minus 2% shear strain, and you will see that in a moment. So let's go ahead and start. In terms of part A, we are told that we have a vertical stress of 3,000 pounds per square foot, a K0 condition of 0.5, and what we would like to calculate in this particular case is the engineering shear strain to yield, as well as the shear stress at yield. So all of these calculations are provided with an associated figure below. First up, in terms of the loading, what we're looking at is shown here. We have this stress, vertical stress, and this particular value is going to be 1,500 pounds per square foot. Try that again, that's 3,000 pounds per square foot. And the horizontal stress is half of that with our K0 condition. So we have those stresses. The shear stress, this is what's going to be changing. So the shear stress is going to be changing, and it's changing because we're shearing the element. The angle gamma xy, which can be approximated as a decimal, is shown here, and you can see that with a height of 1, what we are going to find is that whatever displacement we impose at these upper nodes, so we're going to have, right, here's our single element. We will then have this particular element in simple shear. We are going to be consolidating it, and as I had discussed, this is during shearing. During the consolidation phase, what we are going to have is something similar, but we are in essence going to have rollers on this side. This is going to be fixed like that, and so this is going to move downwards, as you see, like this. So we're going to have these two different conditions. Okay. With the loading, what we are going to have is that the vertical stress is always going to stay the same. What may change, and what we will see change, is that the horizontal stress can change, the shear stress can change, we're going to have rotation or principal stresses, and so forth. Well, the mechanics is described here in terms of the various stress states. The first stress state that I'm showing is in the black. These colors correspond to those in the presentation. But so the black Mohr circle is representative of our state of stress prior to shearing, but after consolidation. You can see here that it has no shear stress, it just has normal stresses, and the normal stress in the x direction is 1,500. The normal stress in the y direction is 3,000. So we start with that. And then what happens is we shear the element, and so the shear stress, tau, is going to increase. It's going to continue it to increase until the Mohr circle touches the failure envelope, and the failure envelope here is defined by that friction angle phi, and that's 32 degrees. And with that, it's going to touch. You can see that I've drawn a little tangent line there. The length of that red, the orange line is going to be the radius of the Mohr circle. And from that, this line, which you see right here, is going to have the same length as this line. And so from that, with some geometry, you can calculate that value is 927. And that is provided right here with these triangles. You go through and you can calculate that the strength at A, our yield strength at that point A is 927 pounds per square foot. We can calculate the shear strain at that particular location. That is when we are yielding. And so then if we take SA divided by the strength at point A, or at time A, divided by the shear modulus, you will calculate that the shear strain is 4.635 times 10 to the minus 4, or that is 0.46%. And so that value has been provided there. Next, what happens is as we continue to load our sample, the principal stresses rotate, and they continue to rotate until we get to point B. At point B, we have the state of stress on our element is such that we have the maximum shear stress, the horizontal stress, and the horizontal normal stress and the vertical normal stress are identical. That is point B. And with the way that we can calculate that is noting once again that that light blue line is the radius of the Mohr circle. It's also going to be the same from the it's going to be the same distance as here. And from that, we can then calculate the strength at B as just, in this particular case, the vertical stress times the sine of phi, and that value is 1,590 pounds per square foot. Okay, so that covers us. So what our expectation is that we should be getting a strength of 927 pounds per square foot at yield. The strength is the strength of the material is going to continue to increase, and it's going to max out at 1,590. The shear strain is going to where the stiffness, where we change from elastic to plastic, is going to be at a shear strain of 4.635 times 10 to the minus 4. So that's our expectation. And so we're going to model this in FLAC, and we are going to get the same results with a few other important modeling considerations and a few other buttons that we're going to need to click to ensure that we're capturing the mechanics well. So let us switch to FLAC now. So here we go. I'm going to do that. So here we go. Okay. So let's start. I have a new project that we're going to create in a new folder. In this particular case, we're going to have one extra grid variable where we're going to be providing the engineering shear strain. We're going to continue to use English imperial units, unclick all of those things, and now OK. Let's place this in a good location. I have added a file, tutorial2, so I'm going to just give it a simple name like tutorial_2. And I could give it a title, tutorial2, as an example. I've went through a lot of the details in class, and so I won't go through them. I'll go through them a little faster than I did earlier. There is one necessary change for us to get some nice response, and I'll show you that once we do the shearing stage. So the first stage that we are going to have in our analysis is going to be consolidation. So we're going to work with one element as before. There's our single element. You can see that it's added this extra one, which is what we would want. And now we're going to go to material and assign. and create, and we could go here, and I could say something like soil. Mohr-Coulomb, that's fine. Density is 4. Bulk modulus is 4.3 e to the 6. Shear modulus is 2 e to the 6. And down to friction angle is 32. And okay, and now we're going to apply it, and then we have that. We would like our element to be, we would like to give our element and our model in general the best initial conditions we can. In this case, we know what those should be. Our initial conditions in our element should be, it should have a vertical stress of 3,000, a horizontal stress of 1,500, and a shear stress of 0. So let's initialize all of those particular values. So in situ, initial, and zones, stress. So we said, okay, we're going to go that initial assign. So that value is minus 1,500. Compression is negative. Vertical stress, assign, and this is going to be minus 3,000. And the rest we will 0. I think, I've never actually used the K-naught before. I suspect potentially what that does is it adjusts one of the other properties. I have not worked with that. Oh, and then also the out of plane stress, we will also make that equal to 1,500 as well, minus 1,500. Okay, and execute. So good, we have those set up. Next, what we're going to do is that we would like to apply a pressure. This is going to be, say, the load that's coming from the piston on our sample here. So let's go to apply and stress and pressure, and just along the top, assign. This is going to be going towards the body, so it's going to be a positive 3,000. Okay, and execute. Good. So next up, we would like the model not to move in the X or Y direction at the bottom, and then we would like it to be able to move freely vertically at the top, but not horizontally. So if we go to fix X, Y, that's going to be fine on this. So this will give us both. And then what we would like is no movement in the horizontal direction at the top. Good, and then execute. What else do we need? I think those are the main items. At this point, we could step for a certain number of steps. However, we can utilize the solve command in FLAC, and it will iterate until it calculates a maximum unbalanced force that is, I believe, less than 1 times 10 to the minus 4. So let's go to that. So run, solve. We don't need these at this point, and then okay. And you can see it takes 2 steps. Let's save that. Well, I'm not sure what happened there. Let's rebuild that just in case. Save. All right, so we have that, and console. That's going to be our first state, but I spelt it wrong. So rename state. Console. Okay, good. A few things that we would like to check. Let's add a few plots. Maybe first up, let's do boundary conditions. That, a similar plot where we have some boundary conditions and some internal stresses. So what would be good? So we are going to add a grid, and under vector, displacement, and under principal stresses, tensors, and stress. So we got those, and then okay. Okay, everything looks pretty good. You can see that it was in equilibrium initially, so there really wasn't anything that interesting that happened. But we do have our vertical stress of 1,300, 3,000 pounds per square foot, and our horizontal stress of 1,500 pounds per square foot, both in compression. So that's good. At this stage, what we're going to do now is shear our sample. So let us do that next. Okay. We're going to click follow. And what we are going to do is, since these are fixed, we are now going to tell the x, which was initially set as 0, is like, wait a minute, no, I actually want you to move, and I want you to move horizontally. At this point, we don't know how far we want to move. We want to move a fair amount of distance here. And so one choice would be is that if we remember that we had a shear strain at yield of 4.635 e to the minus 4, is that we could pick the number of steps such that we get it just to yield. So let's do that at this particular time. But we will continue to increase the shear strain until past yield, until it reaches that maximum, like in the picture that I had included in the lecture notes. So initialize, let's initialize in situ and initial, okay? And with that, we are going to go to GP, X velocity, and then assign. So we want a velocity. Now we could pick something really big, but because this is a dynamic problem, it's advantageous for us to use a smaller velocity, so that especially since we have a plasticity model, so that we don't significantly overshoot the failure surface and aspects like that. So what I'm going to use is 1 e to the minus 5. And so if we use 1 e to the minus 5, and if we remember that our yield shear strain is going to be 4.635 e to the minus 4, we are going to need to step 463 times to just about get to yield. So that's what our value is going to be when we step is 463. We're going to give that a go. Okay, so then, okay. And execute. All right, another thing that we're going to need to do is under alter and then attach. We are going to need to, and this is something that we will only be doing for these single element tests, especially in shear, is that we want the right and left side to move together. And to do this is that we are going to attach these sides. And so with A side, I'm going to go like this, and then with B side, I'm going to go like that. And then I'm going to do assign. You can see that right here. We did not have that in the example that we did in class, which is why if you were to compare the results, you will see some differences. This ends up having the model move in pure shear after, continue to move in pure shear after yield, which is going to be very helpful for us. Okay, so then execute. And I'm actually not sure what the attach will do in the elastic domain. I think it will not make, I think in elastic domain both would not change, but I think then once we get plastic deformations, there are differences, but I'm not exactly sure at this point. All right, so we have that. The other thing that we are going to want to do is that we would like to be able to track the shear strain. Now, shear strain, so gamma XY or the engineering strain, that is not something that is readily available in, that there's not a history for that in FLAC. There's what's called SSI, shear strain increment, which is different. But to get the shear strain, we need to do a little bit of work to do that. And we're going to write a short little script in Fish. So to develop a script in Fish, we start with the define, and we'll give it a function name. So like, create histories. We don't have to tab it or any of those types of things, but it's still good. Now, what we need to do for this to work is we need to create an array. And we're going to give the array name AI for just some array. I typically have used the $sign. I think I was in talking to the folks at FLAC. I think they actually suggested an underscore. So let's give that a go. Underscore. And the reason being is that we don't want to override any of the functions in Fish. there is a video that I provided, which is in the geoanalysis support website on programming in fish. Next is that we want to be recomputing the shear strain through cycling, and to communicate that to FLAC is we need to use the while stepping. So this is going to be executed while stepping. We need to then execute this FSI. So what this is going to do is it is going to grab the strains, the normal strains and the shear strains for a particular element. In this case, we want element 1, 1, and it's going to place them in our array underscore AI. Now what we're going to do is that I am going to store this in my extra good variable. In this particular case, my extra good variable is only for this single element, and so I can use 1, 1, and it's going to be 2 times AI, and 4, the element in location 4, 1, 2, 3, 4 is where the shear strain is located. Epsilon xy will multiply it by 2 to make it the engineering strain, and then we can end. When we use a while stepping, we do not need to continuously, we don't need to then execute the function. It's going to do it automatically. So let's rebuild this, and then I'm going to save it, and I will call this shearing. All right, so we have this. I'll show you how we're going to use this later on, but now we're going to add some histories. So click Edit, go to Utility and History, and now we're going to add some histories. So what do we want? We want to get a bunch of histories for stresses, and I'm going to plot a few. So let's go to total stresses. So let's do horizontal and the horizontal normal stress, the vertical normal stress. Oh, I need to do that, and then I click here, there, and then here, and then there, and then let's do shear stress, and let's also do principal stresses. So that'd be sigma 1 and sigma 2, and that will be good at this particular time. Execute. What we also are going to do is plot the history for in location 7, the 1 through 7. It can be omitted, and FLAC will just automatically determine that, but it's going to be for extra good variable 1, and I'm going to do I equals 1, J equals 1. And now I will go to run, cycle, and what we said was that what we were going to do here is that we are going to step for 463 steps. All right, let's save that. And I'm not sure why it keeps doing that. Save. So what we'd like to do now is create a few plots. First step, let's look at the boundary conditions. We can see that there's been a rotation in our principal stresses. Our vectors are shown right here. The vectors should be the same magnitude and same direction, and that's because we've attached these two sides. The next thing that we would like to do is, let's go to plot, and then history. Well, what would be, let's do stress versus strain. So we would do that versus this. So we have that. So that shouldn't be 5, that should be 6. There we go. That looks better. There's our straight line. And so what we will be able to look at is what expectation is that this should all be elastic, which it is. Well, but how do we check? And so one nice way of doing that is that let's go to the boundary condition, and what we're going to add is another property, and that property is going to be under Mohr-Coulomb is state. So what state does is it tells you whether or not you're elastic or whether or not you have yielded. And as we see here is that our model is elastic. Well, let's see what happens if we go and do another additional cycle. And we can see that during the next step is we have touched the failure envelope, and it is telling us that at yield and in shear. So it is yielding and shear. So we've confirmed that we are reaching yield at about 0.46 at 0.46%. And we can also as print SXY, and you can see that we are calculating a value of 927 if you convert it correctly there. Okay, so we have that, and so let's continue. And so what we'll do is let's go to 2%. So what we're going to need to do here, so let's continue. So what are we at? We are at 2 times 10 to the minus 2. Which is our 2%. Few things that we'll see is that it continues, that's where we get yield, it continues to increase, and then the value that it's reaching over here is, let's see, print SXY, and is 1,590, which is the value that we had calculated up at the top. A few other things that would be worthwhile doing here is let's also add a history where we're looking at all the stresses. It'd probably be helpful to look at them in terms of compression being positive, so we can change that. Also is the principal stresses, let's make that minus as well. And so then we can include all of those, and let's do stresses N as an example. And if you were to look at this and then compare that with the figures that I included previously, what you will find is some consistency between those two. And so then we can save that. Let's see what other important items are there to include in this one. The last one is also, is we created this extra grid variable. We've used it as a history, which is shown right here. What we can also do is plot the results. Right now, it's not very interesting because it's a single value, but if we go to extra and zone grid, I could say something like gamma XY, and I could then click OK. And sure enough, you will see that all the values, there it is right here. Not very interesting. If we wanted the color, so fill, it's going to do a variation, but it's just a single value. So if we go to edit and then block, that'll be a little bit better. So there we have it right there. Okay, that's pretty good. So again, so if I'm going to switch to the tablet in a moment, but so here we have it. So what we confirmed was the results. We do see here's the stress strain relationship where it's elastic, up to the particular point, which we again was 463. So it was elastic in that particular value here. You can use that by the XY is right here, is 4.57 times 10 to the minus 7, 4.57 e to, sorry, 4.57 e to the minus 4, e to the minus 4. And so that's 0.045%. So I'll change that in my notes there. So it's not 0.45%, it's a tenth of that. I had that incorrect there. And then if we go a little farther, so for instance, if we go to 2% shear strain, which is right here, we will get that result. Okay, so I'm going to shift over to the tablet just for a moment here. Okay, so one quick correction is that, oops, needed another 0 there. That down wrong. 0.46%. So that's better. Okay, now what we're going to do is, if we look back, the last problem we're going to work on is, well, a few things. One is, traditionally we've thought, okay, if we have a material that dilates, often we can have an increase in strength potentially, or some type of change in strength. And it's not the shear strength is not increasing because of any change of dilation, because we have no dilation after yield. Instead, the shear stress is increasing because of the rotation of the principal stresses. Principal stresses are rotating. It allows the element, it allows the Mohr circle to get larger. With the Mohr circle getting larger, is the shear stress increases accordingly. The last problem we're going to work on is doing a single cycle of loading for minus 2% shear strain. We've essentially done monotonic loading. We've gone to 2% shear strain. We just want to go back and forth. And so that's not really that difficult to do. One of the nice things is that because we're solving static problems dynamically, we can easily just have a velocity go in one direction, change the velocity in the other direction, and that's what we're going to do next. So let's go back to, I'm going to go back to FLAC. So in doing this, I'm going to utilize the code that we had right here. So I'm going to copy this code and go back to new, and then not new. I want to still do the consolidation phase. I'm just going to go to follow, and I'm going to paste it right here. So just to get us started, I'm going to rebuild it and save it. And I could call it, I don't know, cyclic shear as an example. So in looking at this problem, what we did is we went in one direction. All we need to do now is we are going to change the sign of the velocity and go in the other direction, but we need to go a total of 2%. 2 plus 2 is 4% in the other direction, so we're going to change the initial velocity. So one thing that might be nice is to get this all together is I'm going to cut this, put it right here, and add a comment. So this is going to be the first quarter cycle. And now I'm going to do a half a cycle in the other direction. And so minus, and then cycle 4,000. So let's see if that works. What did I do wrong? Oh, I spelled it wrong. So cycle. So what you can see is that here we go. We loaded it. It was loaded. It yielded. And then there was that rotation of the principal stresses. Then here we changed direction. It was elastic, and then it was plastic to here. And so now what we're going to do is that we could go, and if we just change it the other direction, we could either go to right here, which we'll do, we could do another quarter cycle, which would be just copying that. it will do the last. And so you could see that it's gone a full cycle all the way around, and this could continue. When we are working with UBC Hist and PM4 sand, we will be using a script that was previously developed, but in essence, it's doing the same thing as what we have right here. So we can go to, let's save that. And if we wanted to, maybe I could rename this branch if I wanted to. I could say, monotonic shearing, and rename cyclic shearing. And maybe if I also, I could rename the branch monotonic and cyclic as an example. And save that, and this project file will be contained in our shared Dropbox, as are the others.